In this video, we're going to go over section 6.4 from our textbook, which is more on logarithmic functions. So we'll start with this fact here. This exponential function here of this form, a to the power x, is a one-to-one function, and therefore it must have an inverse. In fact, the inverse of this exponential function is the log function, log base a of x. Now we know from section 6.1 that we can find the inverse of a function by solving for our variable x and then switching our variable x and y. This is because, if you remember, this is a useful chart from section 6.1, but the domain of our function f is the same as the range of our inverse, and the range of our function f is the same as the domain of our inverse. So when we want to find the inverse, we have to switch our inputs and outputs. So we switch our x and y's. Doing so, we find that the inverse function of this exponential function is our log function. And this is probably not a surprise based off of the inverse properties that we saw in section 6.3. Something else that I wanted to note though, in section 6.1, when we found the inverse function, what we did first was solve for x and then switch our x and y variables. In this case, it looks like they switched x and y first and then solved for y. I just want to make a note that we can do it either way. You'll get the same answer. Additionally, we know that if two functions are inverses of each other, then taking the composition of these functions will give us x. And same for taking the composition of these functions. And so we see that that is satisfied. So let's look at an example here. We're given this exponential function, and we want to find the inverse of this function and graph both our function and the inverse function. So we'll start with our steps for finding the inverse from section 6.1. So first we rewrite our f of x as y, and then we want to solve for x. So adding 6 on both sides of our equation, we get 4x, and then in order to bring this x down, we have to take log base 4 on both sides of our function, because we know that these guys are going to undo each other. So we end up with log base 4 of y plus 6 is equal to x. Now the next step that we have to do is switch our x and y variables. So this tells us that log base 4 of x plus 6 is equal to y, and therefore our inverse function, written with this notation here, is log base 4 of x plus 6. Alright, now we found our inverse function, and now we want to graph both our function f and this inverse function here. Well, we can do this by remembering what we went over in section 6.2. If we have an exponential function of this form, this is what the graph looks like. Our domain is all real numbers, and our range is all positive numbers greater than 0. We have a horizontal asymptote here, and the graph passes through these 3 points. So we'll use this information to actually graph the parent function of this guy, and then use our graph translations in order to graph this guy. So first, let's graph this guy. Based off of this information here, we know that our graph is going to cross through the point -1 and a to the -1 power. Our a here is 4, so 4 to the -1 power is 1 over 4, which is 0.25. So our first point here is going to be -1, and then 0.25. So right about there. Our next point is going to be 0, 1, so right about there. And then our next point is going to be 1, a, and in that case our a is 4. And we have a horizontal asymptote, the x-axis. So our function looks like this. Sorry. I'm trying to make this a little nicer. Alright, then we can use graph translations to graph 4 to the x minus 6. So in this case, this is going to be our graph 4 to the x shifted 6 units downward. So this is, and then shifting these 3 points 6 units downward. First, we'll shift this one 6 units downward. So that'll be 1, 2, 3, 4, 5, 6. That point will be right about there. Doing the same with this point here, minus 1 and 0.25. We'll get this point here. And then shifting this one 6 units downward, we'll get that point there. And since we shifted this guy 6 units downward, our horizontal axis also shifted 6 units downward. So right here, at the line y is equal to -6. So our graph here for our function f is given by this guy here. All right, now we know we want to graph the inverse of our function 4 to the x minus 6, and we saw that that was this log function here. Now, before we introduce any log functions of certain forms, we know that the inverse function is just our x and y values swapped, right? So, for example, this point here is 1, comma, -2. This point here is 0, comma, -5. And this point here is -1, comma, -5.75, because we're at 0.25 and we move 6 units downward. So if we want to find these 3 points for our inverse function, all we have to do is swap our x and y values, our x and y coordinates. So for example, if we have 1, comma, -2, we will have -2, comma, 1 here. So just swapping our x and y coordinates. Similarly, we have 0, comma, -5 here, so this tells us the point -5, comma, 0. Our graph will intersect that point as well. And then lastly, switching the x and y coordinates for this guy, we'll have -5.75 and -1. So right about there. All right, so this tells us our graph will pass through these points here and look like this. Okay. So that's how we can graph our log functions if we are given our exponential function. Now, this brings us to some properties of log functions of specific forms. So if we have a log function of this form here, then we have these properties. This will be our domain and range values. This is what our graph looks like, and it will intersect these 3 points here. We'll also have that the y-axis here is a vertical asymptote, so our graph will not touch this axis here. So, similar to what we did for section 6.2, we'll look at some examples of log functions of these forms and others, and then use our properties along with graph translations to graph our log functions. So for example, if we want to graph this guy here, what we'll use is we'll use the parent version that is of this form here. So what we want to first do is graph this guy and then use our graph translations. So we know we're going to have a vertical asymptote on the y-axis. We also know that our function is going to pass through the point a to the -1, comma 1. In this case, a is 3, and 3 to the -1 is 1/3, which is roughly 0.33. So this tells us we're going to have a point at 0.33, comma -1. So that'll be right around there. We also know we're going to pass through the point 1, comma 0. So right there. And then a, comma 1. And in this case, a is 3. So 3, comma 1 is right about there. So this is our graph, log base 3 of x. All right. Now, if we want to graph this guy, we know it's just going to be this function here shifted downwards 1 unit. So graphing this guy here, we're just going to shift these points down. So for example, this point's going to be shifted here. This one's going to go here, and this one's going to go there. So our graph looks like this here. All right, let's look at another example here. We're looking at a log function of this form, where our base A is now between 0 and 1. In this case, this is our domain and range. Our graph looks like this here. We still have our vertical asymptote as the y-axis, and our graph is now going to pass through these 3 points. So let's do an example of this here. In this case, we don't have any graph translation here. So we know our graph's going to pass through these 3 points. The first being a comma 1 here, or a is 1/2. So we're going to have a point at 1/2 comma 1 there. We also know we're going to pass through 1 comma 0, so that'll be that point there. And lastly, a to the negative 1 comma negative 1. Well, in this case, our a is 1/2. Raising that to the negative 1 power gives us 2. So we're going to have a point at 2 comma negative 1. So right about there, and our vertical asymptote is our y-axis, so we're not going to cross that guy. All right, let's look at another example. Let's say we want to graph this natural log function. We can see that we have ln of x plus 2, so we do have a graph translation here. We're going to be moving 2 units to the left. But first, remember that we can rewrite this guy in a familiar form. Ln of x is just log base e of x here. So this tells us that if we have ln of x plus 2, this is the same as log base e of x plus 2. So what we can do is use this information here to graph this guy. We have log base e of x in this example, and e is just a constant. It's roughly 2.7, so it satisfies this here, and so our graph will behave like this here. So the first thing that we're going to want to do is graph our parent function, this guy here. We know that we're going to have a horizontal asymptote for our y-axis. We also know that our function is going to pass through these points here, or our graph is going to pass through these points here. So first, we have e to the negative 1 power. This is approximately equal to 1 over 2.7, which is approximately 0.37. So our first point here is going to be 0.37 comma negative 1. So right about there. Our next point is going to be 1 comma 0. And then our last point is going to be e comma 1. And so e is roughly 2.7, so that'll be right about here. So this is our function log base e of x, which is the same as ln of x. Now to graph this guy here, we're going to use this information and do our graph translations here. Like we said, this means that our graph is going to move 2 units to the left. So this tells us our vertical asymptote used to be the y-axis is now going to be the line x is equal to negative 2 because we're moving 2 units to the left here. Additionally, each one of these points are going to move 2 units to the left. So for this one, we'll get this here. We'll get negative 1 comma 0 here. And then for this one, roughly that point there. So the graph of our natural log function, make that a little nicer, looks like this guy here, intersecting these 3 points. All right, let's look at another example here. we want to graph this function here, e to the x minus 3. So what we'll do in this case is again use our parent function here. We have this exponential function e to the x here. And again, from section 6.2, we know functions of this form, a to the power x, behave in this way here. And remember, like we said, e is just a constant, so that satisfies this here. E is roughly 2.7. So we'll use this information to graph this guy here. Then we'll translate this guy 3 units down to get our e to the x minus 3 function. All right. So again, we know that our graph is going to intersect these 3 points. From the last example, we saw that e to the negative 1 was about 0.37. So our first point is, let's keep the color coding consistent. We're doing blue here. So our first point is going to be negative 1, comma 0.37. So that'll look something like this here. Our next point is going to be 0, comma 1. And our last point is going to be 1, comma e. So that'll be roughly about here. All right, so this is our graph from our function e to the x here. Again, we have our horizontal asymptote as our x-axis, so we're not going to cross this guy. Now, to graph this function here, we're just going to use our translations. So these 3 points are going to move 3 units downward. This also means our horizontal asymptote is going to move 3 units downward. All right. So we'll have this point here, about this point here, and this point here. So this is our graph for our function e to the x minus 3. All right, and then the last thing we're going to look at here is some examples for finding the domain of log functions. So we've seen from the previous videos that for both the common log function and the natural log function, the domain is going to be all positive real numbers. So the argument here for our x is going to be greater than 0, it's going to be positive. So let's look at these 2 examples here. We want to find the domain of each function. Now looking at this part here, we have log base 2 of x minus 1. So in this case, our argument is x minus 1 here. Remember, our argument must be positive. So this tells us our x minus 1 must be greater than 0. Okay? We don't care about our base here. We just care about the argument being greater than 0. So this tells us x must be greater than 1. So our domain is going to be from 1 to infinity. All right. Similarly, let's look at this example B here. We have log base 3 of x minus 1. Now in this case, the only argument we have is this x here. So we don't really care about this base, like I said, and we don't care about this minus 1 either. This minus 1 is not part of our argument. Our argument is just x here. And we know that our argument must be positive. So in this case, our domain is just going to be all numbers greater than 0. All right, so that'll be it for this video.